All right, good afternoon. Get started. Okay, first, I'll hand out the page, just a survey, quick questions. Basically, we already went through a couple of chapters, homework, exams, phases. So I just want to see if you have any feedback, any comment. You can say anything bad, the same, that's why I call it modulus point. So anything you're not satisfied with, put it there. And I don't need your name, so it's anonymous. So don't put your name there. I don't care who said it. I just want to get some feedback. All right. Okay. Yeah. You can give back to me after class. So I don't need it right now. Let's pass around somewhere. There should be more copies. All right. Okay. Take your time to do it, but I want to go ahead and start it. All right. So last time we talked about stress in a beam. So when you have a beam that ends bending, and then there's going to be normal stress, right? Remember we use this form to demonstrate when you bend the beam, right? So you're going to see that one side to be stretched, the other side get compressed. So and the lines, if you see the cross sections, remain as straight lines. So the plane remains as a plane. So we have the plane assumption, right? So based on the plane assumption, then we look at how does the beam deform, the geometric relation. Figure out what's the length change here, what's the length change here at any location y. Then we figure out the stress, right? So you can figure out the strain, then multiply the modulus, you get the stress, right? And then we do the integral, link that to the moment, right? We talk about pure bending situation. Okay, so here is actually the equations. All right, so we have the strain, the curvature, how much you bend it, right? A straight tube, once you bend it, there will be a curvature. So that's one row, and we find it. And then this stress actually can relate to the moment, right? So in general, if you have a beam, you know the moment, then you can figure out the stress. Okay, so today we're going to continue along this line, talk about how to find the maximum stress, because that's what we care, right? Where is the failure going to occur? How much you can load the beam, right? When you design a structure using beam, right? Or like can be a beam, or can be, you can say it's for biomedical engineering, you can say it's a piece of bone, right? Or a piece of artery, or a piece of muscle, right? Anything in the body and the bending, then how do you determine where the maximum stress is, right? Because everything in the body, when you move around, there will be bending as well. Okay, so first, let's say, how can we find the maximum stress? Right? We mentioned that a little bit. Okay, so we have this stress equation here. Right? So stress equation given right here. That's the sigma x equals mi over I. Right? So the y is the distance. Okay, so with that, where is the maximum stress when you have a beam? If you look at given cross-section, you will be either the top edge or the bottom edge, right? Never in the middle, because middle is zero stress actually, right? So stress is actually zero. Okay, so for this reason, so we just need to find out where the y maximum is. Then you're going to have maximum stress. Okay, here again, when we talk about stress, maximum, we don't care it's compression or tension. So for rectangular beam, the two side, compression, tension, we just treat it equally. Whatever the value is biggest, we take that as a maximum. All right. Although in reality, material are different when you put it under tension and the compression. Okay. So here is how can we make it this equation a little easier to find the maximum. So we say always you find the y maximum, that gives you the maximum stress, right? So if I can write it here, so the sigma maximum, that's what we're looking for. Supposed to be as given this equation. So you want to find where the maximum moment when this is the maximum, right? And then the y takes the maximum. Of course, I should be the minimum, but we talk about uniform beam, right? So I is the same everywhere. So therefore, this is a constant when you look at the different locations. So the true maximum stress should be given by m maximum times y maximum. Right? So y maximum, when you give a cross section, let's say you have this cross section here. When you bend it, this beam, a circular beam, When you bend it, y maximum will be always either this point or this point, right? So because we know the neutral axis will be here. Now if you have let's say you have a triangle, the center is here, so the neutral axis is here. Therefore, where is the y maximum? The top tip, right? So it's right here. This distance is the y maximum, right? And if you have a rectangular, then the y maximum will be this distance or this distance, right? It's equal because the rectangular, they're symmetric. Okay, so one point here, what I'm trying to say here is, when you talk about y maximum, it's a character of the geometry, of the shape of the beam, cross-sectional section shape of the beam. So when you give a shape, then that y maximum is given. It's set, right? So y maximum is actually a character of the cross-sectional shape, right? And okay, remember what's I? What's the I? Moment initial. That's a character of the cross-section also. So it's a geometry determined or dependent parameter. Has nothing to do with your load, right? So for this reason, we can actually combine these two terms because they all depend on geometry. So I can call this one, we call it section modulus. So I change this to M maximum over the section modulus, S, right? Because the character is a parameter related to the geometry. So for any given shape, you can always find the I value, the moment initial. Also, you can find the S value. So for this reason, you can set up a table in advance. Okay, all different given shape, what's the I value, what's the S shape, what's the S value, right? So when you do the calculation for maximum stress, it's much easier. So you just use this equation, right? So just simplify one step. That's it. Fundamentally, it's the same thing, right? You put the y maximum there, you put the I value there. Okay, but just one step easier. And so in the textbook and actually engineering manual, you can always find for giving cross-sectional shape, an I-beam or rectangular beam or circular beam, you can always find the I value, and also you can find the S value. So you can just directly use S value to calculate. All right. So here next is actually break down what the common shapes that we talk about. What's the I value? What's the S value? This is in the textbook. All right. So so you don't have to copy everything. All right. So you can see here for rectangular, this is 1/12, but the S, because you divide in half edge, that's the y maximum. So you get 1/6. Right. So the only point I want to make here is oftentimes people get confused when to use the I value, when to use the S value. All right. And get the equation confused. I mean, they try to calculate the I, but they use the S value. Say, for example, for this one, they say I equals 1/6 of BH cubic. Right? When they calculate the S, okay, they say H equals, the S equal to 1/6 of BH cubic. See here, this is a square. All right, this is a cubic. So they are slightly different. Just need to pay a little bit attention which one you're using, what's the correct equation. Right? So don't use the wrong formula, that's it. Just a little bit careful there. Okay, then for circular, we have this I value, so the S will be there. And the other shapes, you can search the table in the textbook, and you can find all the values for I beam, everything. All right. Okay, so with this, the calculation of maximum stress is really easy, right? So you always, the maximum stress equal to M maximum, and then over the S, the shape, right? Okay, so next, we're going to go over just a couple more examples to say how can we determine the maximum stress and where is this maximum stress. Okay, for two purposes. One is we learn this new content, right, kind of practice. Secondly, we want the VM diagram, help you review the VM diagram. Okay, so if you get the wrong VM diagram, you may find the wrong maximum moment. Then you get your calculation will be wrong. All right, so here I have a couple examples. So let's say we pick one. I don't think we can go over all the three. So I'll go over it. You guys pick which one you want to go over. Okay, the first one is this one. Second one, there are two movements. The third one is you have a distributed load Q, overhanging. So which one you want to start with? We just go over one first, then say the time. The very first one? The double movement? This one? This is the second one. Okay, so we go over this one first, and then if we have time, we'll do the other one, the overhanging one. All right? Okay, the simple beam maybe a little bit is simple, right? So let's do the overhanging next. Okay, for this one, we have here M applying here. Then you have a 2M1 applying here. Okay, let's give a value. I think with a value, it's easy to do the calculation. Okay, so here's 2 meter long. Here's 2 meter long. Here's 2 meter long. Okay, give a M a value. 10. Okay, we like 10, right? So 10, then this will be a 20 here. All right? Okay, so the question, we know, what's known? We know all the load, we know all the dimensions. Okay, but for calculate stress, we need to know the cross-section, right? What kind of cross-section you want to give? Rectangular? Okay, rectangular, then we need the height and the weight. Okay, let's say this one is width, maybe say 2 centimeter. All right, and then the height, give a height value 4. Okay, 4 centimeters here. All right, so maybe I need to draw it a little bit better, proportional. This is the one. Okay, so that's the cross section of the beam. We need to find out where the maximum stress is and what is the maximum stress. Okay, that's the goal. And we know you can calculate max stress, right, by this equation, M maximum over S value. Okay, can we determine the S value? Yes, right? So that's the easy part. 1/6 of BH cubic square. Okay, okay, square. All right, so it's easy. You know the B value, that's 2 centimeter. H value, 4 centimeter. So you plug in, you calculate. All right, so the key now become determine the M maximum. Okay, how to determine the M maximum? You need to survey the whole beam, right? Basically, you draw the VM diagram, find out where the maximum movement is. Okay, to draw the VM diagram, what's the first step? You need to find the reactions, right? Step 0. Okay, so reaction RA here, RB here. That's a free body diagram. Now, find out RA, RB. Sigma, what? Fy equals 0, right? So sigma Fy equals 0. Okay, translate. RA plus RB equals 0. Okay, so RA must be opposite direction with RB, right? There will be opposite direction. Okay, that's one equation. Another one. Summation of moment to any point should be 0. Let's pick one point. A. Okay, so sigma M to point A equals 0. All right. Okay, now translate it or express it out. To point A, so you're going to have M1. M1, that's what we call negative, right? We use counterclockwise, so we assume this is the positive direction for equilibrium, right? Okay, so you have negative M1, negative 2M1, then plus RB times the whole length, that's 6, equals 0. Okay, now what's the RB? So RB will equals to, so there will be, this will be divided by 3, right? So you have 1/2 of the M1. Is that correct? Say 3M1 equals 6 RB. So RB will be half the M1, right? Okay, so equal to 5. Okay, so this will be whatever the unit we use. Newton, if this is a Newton meter, then this will be Newton. If this is a kilo Newton meter, then this will be kilonewton, right? Okay, so for now, we just don't pay much attention to the unit yet. But for the exams, you need to pay attention for the homeworks, right? Make sure you have the correct unit. All right, so we know RB equals to, this is RB, right? I'm writing kind of weird. All right, RB equals 5. Now, what's RA? negative 5. So that means this part you have this way 5. This part you have upward 5. Okay, now the VM diagram. V. What's the VM diagram? Okay, so start at 0. Okay, actually I need to change the line. I'll put the axis here. I'm out of space. So this is the axis. All right, so start 0, then you go down 5. Then you keep going. Now you see a counter movement, jump. No, there's no counter force, so force don't jump. So just keep going until here. Oh, C5, you go back. So basically a constant shear everywhere. All right, now next M. Okay, so I draw the line here. This is the X. Okay, this is the M diagram. This is the V. All right. Now, once you start, you see a constant force immediately. So, how would the M change? Jump? No jump. Okay, so you just continue change. Okay, so you either go this way or this way. Now, which way? Down, because you accumulate negative area, right? Okay, once you here, you see this constant movement. Therefore, from this point A to this point B here, actually don't call it C here. Okay, how much you change? The movement change? That area, right? So area should be 10 times 2, 20. So you, right? Oh, 5, sorry. 5, right? 5 times 2. So that's 10. So you go down 10. All right, so go down 10 here to here. Okay, now at this point, you're negative 10. Okay, now what do you see? You see a constant movement. So that's a moment for movement to jump. Okay, you jump. Which way? Up. 10. Oh, back to 0. Okay, now, then what do you see? You see this accumulate more negative area. So what happens from point C to point D? You go down by 5 times 2 again. So you go down to 10. Right? Okay, now you see another movement. 2M. That's 20. Jump. Right? Which way? Up or down? Anyone say down? Up, because it's this way, right? Imagine you're going this way. Now you see a movement that's bending. Actually, I should show you this way. Okay, you're going this way, right? Now you see a movement bending this way. That means you're going to bend this part of beam upward. That's a positive movement. So therefore, you go up. That's how you kind of physically you imagine. Okay, so you go up by 20. So you'll be here. Okay, now what happens after you pass this point? You start accumulate negative area again. And how much you accumulate from point D to point B? Negative 10, right? So you go down by 10. So that's the. All right. Okay, now anyone got a different curve? No, we're on the same boat. All right. So now what's the maximum movement? 10, right? Where? You can see here, negative 10, or positive 10. So it will be both point C and point D, right? We call this point C, this point D. All right. But for this one, luckily, it's the same value. So you can say either one. Okay, what if they're different? What if the point C and point D, the value are different? Which one you pick? The highest one. Doesn't matter if it's negative or positive. You pick the highest value, the absolute value. Right? Okay, so for this case, M maximum equals 10. So now you plug in, you'll get the stress. Right? Okay, so basically with this equation, we can always determine what's the maximum stress in a beam if you know the load. Right? Okay, now can I change the question a little bit? Let's say I have this beam here, right? I want to support this much load. Okay, I know I'm going to select a steel material or a wood material, right? And so I know their stress, their maximum stress, sigma yield stress. And I want the safety factor of, let's say, sigma y equals to 200. Just give a random number. Okay, I want the safety factor of 4. Okay, so n equals 4. Now, can you design a beam that I can use here to carry this load safely? Yes. So now you know how much stress you can go, right? How much the stress can go up. So your safety stress, sigma, what we call allowable, right, will equal to sigma y over n. So that's basically 50. So you know I can allow the stress go up to 50. So I know the stress, right? And I need to find a beam that can carry the stress up to 50 with a safety factor of 4 there, right? Okay, now what you can do to design this beam that fits this need, right? You go to Home Depot, find the beam with certain dimensions, right? So what the dimension you can select? You can select the S value, right? The section modulus. So you know the stress can go up 50. You know the maximum moment is 10. So you can, from this equation, you can determine what's the section modulus you need, right? Once you know the section modulus, then you can find, okay, there are maybe a different beam that have this section modulus value. So you can say, oh, I want a circular beam. Then you say what the diameter should be. You can calculate, right? At what diameter the section modulus is this given value, the needed value. Or give you a rectangular beam, right? Or give you just a square beam. So you can determine the size, the dimensions. Okay. So this basically become a design problem. So when you go to senior design, you're going to design things for the function. So you can basically determine, okay, what size of beam I'll need to carry this load to be safely be able to use here. So that will be the design, right? So that's the second type of problem. Okay, the third type of problem can come from determining the load. Let's say I know this beam. Okay, the side is 2 by 4, right? And then I know I have this loading limit is 50. The right stress can go 50. Now then I can ask you how much moment or how much load, force I can put there. So that basically determines the loading limit, right, of the structure. It's similar to chapter 2. When you have a cable, right, you can say, I know the material, right? I know how much stress you can go, and then you determine how much load you can apply in there. Right? So it's similar, 3 type of questions. Determine the maximum load you can carry, determine the maximum stress at the given load, or determine the dimension you need to carry the load. Right? So that's all 3 type of questions you should be able to handle. It's the same thing. The equation, the relation is the same. It just asks you different variables. Yes. So it's 3 here. Let me just write down this again. Let's see, use the next one. Okay. So you have this sigma maximum here equals to M maximum over S. So there's 3 variables, right? I can give you any 2, ask you to design, find out the third one, right? First one is given load, given a beam, you determine the stress. Then you say, oh, it's safe or not safe compared to the material limit. That's the first one. Second one, I give you the beam, so you know the section modulus, and I know the material, so I know the stress limit. Ask you how much moment I can apply there. What's the M maximum? Right. So the third one will be, I know how much stress it can go, how much moment I'm there, and then ask you to select the section modulus, design the beam. So that's the 3 type of questions. In homework, I think there are all 3 types can come to you, right? Similarly, in the exam, I can ask you any one type of this question. It's the same relation, right? If you know the key is this relation, then it doesn't matter which one they ask you. You just put the equation there, right? Punch the number, then you find the answer. All right? Yes?
Can you go back to the other slide real quick? Kind of a question about the M map.
Yeah.
You say our M diagram there. If
Yeah.
at point C, now the negative 20, and at point D.
No, point C is negative 10.
Right, but I'm saying if it were negative 20
Yeah.
and D was 10,
yeah,
we would take negative 20 to
you negative 20. Yeah, because the movement, positive and negative, just bend in different way.
Okay.
Right? What matters is actually how much you are putting stress there.
Okay.
Right? If it's positive, you are compress the fiber on the top, stretch here. If it's negative, you stretch here, compress here.
Right.
That's the only difference. So from safety point of view, doesn't matter positive and negative. That's why. Yeah.
Sign convention doesn't matter. We use absolute value. So it's going to matter later
Well,
on.
for the maximum, the sign doesn't matter, right? Because you just determine the location, right? Okay, so actually here's the point. So for this one, for example, right, where is the maximum stress? The positive will be here, right? And then the negative will be here at the top. If you have a negative movement, right? Let's say this one, it will be opposite. So basically, the top and the bottom, one will be compression, one will be tension, right? Depending on positive and negative, that's basically the difference. Right? So positive and negative change the location of the actual, the point where the maximum tension occurs. But for safety, doesn't matter, right? All right, that's a good question. Any other questions or comment? All right. Okay, for those coming in late, we have a survey sheet there. You don't need to put your name there. Just say any problem, complaints, you put it there. All right. Because for other classes, students have complaint, they can come to me as department chair, complain. But I'm the department chair, so if you complain to me, it's directly to the chair. So of course you can go to dean or president, right? But most of the time you don't need that. If you need, I can just black my eye. You just say, I don't know who said it. Complain. That's basically the way you put down there. Okay, or I can turn around, right? Whoever complains, then become department chair, you just complain. All right. But anyway, I just say if you have any feedback, actually help us improve the class, right? Okay, any other questions on this problem?
So we can expect it to fail like policies?
Yeah, I think they will fail if in real case, I mean not in real case, in theory, it will fail both point C and D because they have the same load, right? And to me, actually, maybe most likely it will fail at point D because D are stretching this side positive, this side negative. But based on the theory, it's supposed to fail at C and D simultaneously for this problem. Yeah, you have a question?
Well, I was going to ask if there's a continuation of her question. Since there's a very large discontinuity at that point,
yeah.
does that hold loading implications for a beam that's loaded this way? Like the fact that there is a moment of equal magnitude being applied both in the negative and positive sense at point B, can that be phrased as a question somehow?
That actually no, because remember, if you look at the point D locally, right? Because you have a constant moment applied there. So things are pretty non-uniform. You have a jump there, right? So, but that's a local effect. So in this class, we ignore all this local effect. We just look at the majority. Remember, we talk about long beams. So we look at the majority part of the beam, not the transition point. Right? So for that reason, we're not going to detail, okay, what's happening at this point there. We're not going to look at that detail. So basically, we'll find out where the M maximum is, and then use that to calculate the stress. Okay. Any other questions? Okay. We have plenty of time. Then I think we can go over one more example. Right. So you want to go over this one or the other one? This one? Okay. Again, let's give a value. I think with value, it's easier to illustrate. Okay, Q. Yeah, we can try. Okay. Or you can come to me, we can talk about one. Basically, non-uniform is similar, right? It's just mathematically, when you calculate the total force, it's just a little bit, it's not this length times the magnitude anymore, right? You accumulate, so basically this minimum, maximum, you combine half of it, and then you calculate the total value. All right. I think we may have one homework problem that's not uniform. Maybe just only one problem there. In the exam, it won't show up because just calculation-wise, just a little more, but concept-wise, it's the same thing. Right. So as long as you know how to handle the uniform beam, I think just for this class, it will be okay. Of course, in real world, you're going to have all kind of variation of the distributed load. Right. Okay, so give a Q value here. Let's say 10 again. All right, 10. Okay, we need the length. Maybe 4. 4. Okay, then this will be 1/3. We'll give it here 2. Here 2. That's okay. Or you want to change middle to 6? Okay, change middle to 6. All right. So I don't know what's the result. You need to be careful with me. I may mislead you to a wrong answer, right? You need to be careful now. All right, so now your responsibility check, we're doing it correctly. Okay, so we have this dimensions. Of course, this cross-section, we know it, right? So now again, the main thing is find the M maximum, right? Once you find the M maximum, you just use this equation. So our focus will be focused on getting the M maximum. All right, how to get the M correctly? M maximum. In the VM diagram, right? Okay, so you're going to have, what are you going to have here? RB, right? You're going to have RC. Okay, now what's RB? What's RC? Sigma Fy equals 0. So, let me write sigma Fy equals 0. And then you have RB plus RC equals 0 minus Q times 10, right? Q times 2 plus 6 plus 2, so that's 10. The total length equals 0. Okay, so RB plus RC equals to 100, right? So this says RB plus RC equals to 100. All right, we need another equation. Okay, here's the trick. Can we find RB, RC here without writing another equation? What's RB, what's RC? 50-50. Why is 50-50? They are evenly distributed, symmetric, right? That saves you time. So RB, RC, 50, all right? So once you are experienced, you can quickly sometimes get answers, right? But at the beginning, or if you're not sure, write the equation of equilibrium, find it correctly, right? Okay, so 50-50, we know now, so this will be 50. 50. All right, so now what's the V? What's the M? Okay. Start 0, right? End 0. And then here you see a country force. Here you see a country force. This point, this A, this point B, this point C, and this point D. All right, start 0, end 0. I will draw this point. Once you start, what do you see? You see a distributed load. Now you don't see 0. You see a distributed load, right? Distributed load. All the small forces pushing downward. Like you have a lot of small p's, p value pushing down, right? So you go down this little bit, down a little bit, down a little bit, right? So basically, straight line, you go down, right? Or in other words, you are calculate this area. You change by this area, right? Integration of V, integration of Q equals V change with negative sign, right? So this one, so it'll be how much you going down totally from point A to point B. So it'll be 10 times 2, so that's 20. So here I have negative 20. Okay, once here, I say a concentrated force. So force will go up, follow the arrow, right? Go up by 50. So I end up at the 30. Right? Okay, past this point, I say distribute load again. So I should just, right? Q constant. So this will be sloped line. Going, right? Okay, now from point B to point C, how much I need to go down? That will be this area, right? Again, this area. Okay, how much is this area? 10 times 6, 60. So here should be negative 30. Because I'm going down 60. Okay, now I see a concentric force again. Go up by, or down, up by 50. So where am I? 20. Okay, now say distribute load again. So go down 20. So a straight line goes back to 0. So start 0 and 0. All right. Yes.
Do we ever need to label that middle point where H and time?
This part. Yes. You're going to need it. Okay. The reason is that's the point. What happens? M take maximum. See, we're looking for M maximum. So you're going to need it, right? So therefore, it's important you need to be able to find out where this point. Okay, can you find out where this point is? Okay, how far from point B? Let's call this one point Q. Okay, where's point Q? 5. Right? For this one, there are multiple ways you can find it. For this one, symmetric. So right in the middle. That's the easiest way you can say for this problem. But for a lot of situations, you cannot use the symmetric because it's not symmetric. Then you just need to find out, okay, this value here, what's the slope here? This triangle is proportional to this triangle. And you know the total is 6. So then you do the division, how much it should be there, right? They're proportional. And so you find out this distance, let's call this x, so you can find x. All right? That's a general rule. You can use it. For this problem, somehow special, they're right in the middle, symmetric. So immediately that's. All right, so that's the Q. Sorry, that's the V. Now what about M? Okay, what's the M then? Start 0, end 0. Okay, once you start, what do you see there? You see a distributed load. So you accumulate negative area at an increasing slope. So what kind of curve you have? Parabolic, right? Okay, it's a negative, right? You accumulate negative area, so the must be going down. But is it this way going down or the other way, concave? It is this way, right? We always say if Q is pointing downward, then the concave will be this way, right? So this is the correct way. So you'll go just like this here. Another reason you can kind of tell whether it's this way or the other way, because you can see here, initially at the beginning, you accumulate this area. Every step you accumulate smaller area. Here, every step you accumulate bigger area, right? So here you decrease slower. Here you decrease faster. To speed up, that's why you have a parabolic curve going this way. Okay, that's another way of helping you. Okay. Or if you just want to memorize it, you say, okay, Q point downward, you have this kind of. But if you want to understand it, you say, okay, here you accumulate negative area faster and faster, so it must be this way. All right. Okay, so here, what's this value? Negative 20? Or negative 40? Should be this area, right? Change of the moment is the area of the V. Okay, from here to here, this triangle, what's the area? How you calculate the area of triangle? Anyone has a difficulty? Should be 20 times the two sides, times 2. That's 40, but it need to be half. So what's the value? 20, right? Okay, negative, right? because it's negative area. All right, once here, now what do you see? You see a contrary force. Should M jump? No, no jump. So no jump, then you just go this way or go this way. Now you go which way? Up. Why up? Because you now accumulate positive area, right? So you should go up. Okay, now at the beginning you accumulate a lot of positive area. Then gradually you accumulate less amount. So therefore the curve should go like this. At the beginning you go increase very fast. At the end here you go much slower, right? Okay, at this point, what's the slope here of the movement? 0, flat out, because V is 0. Okay, now this is the shape. Now what's the value? What's the value here? Should be changed from point B to point Q. Should be the area of this triangle. Okay, what's the area of this triangle? Should be 30 times 3, right? So that's 90, half, 45. So you should go up 45 from negative 20. Okay, now where you are? You're at 25. Okay, so 25. All right. Okay. Next. Okay. Simple way is symmetric, so you can just draw the second half. That's the quick way, right? But in general, it's not symmetric, so let's just do it. Okay, so now once past this point, you're going to accumulate negative area. Slow at the beginning, faster at the end. So we'll be going like this. All right, how much? You change from point Q to point C. 45 again, another 45. Okay, so you're back to negative 20. Right? And then here, you accumulate this area again, so you go up 20. All right? Now, do we have an answer? What's the maximum moment? At point Q. Right? We not only know the maximum, we know where. So we know right here, so the M maximum is 25. Right? So, can you determine the maximum stress? Can you check it's safe or not? Yes. All right. Okay, any other questions? Where M is 0. Okay, so does this mean anything where M is 0? For safety, maximum doesn't matter, right? Right? Okay, now what's this point? What does it mean? M is 0 here. That means there at that location there's no bending. So that part of beam, no bending. What I mean? Will remain straight. So if you look at the slope of the deformed beam, where M is 0 should be straight. At that location, no bending. Okay, you'll see that more when we talk about deformation of the beam. Okay, so for now, M0 doesn't mean much. Just say M is 0, no bending, right there. Okay, other questions?